In this short video, we will introduce the idea of resistance. Just first a recap on what we did in the previous videos. We talked about current. So current is the rate at which charge moves. As I said in those videos, we had been talking about mostly static situations, but now we're talking about when charge is moving or flowing. And of course, the big application of that is electronics and electricity flowing through wires. So we want to talk about current. Current is the rate at which charge moves. It is the letter I is used for current, and the definition is it's the derivative of charge with respect to time. So it's change in charge. It's an amount of charge divided by an amount of time. The units would then be coulombs per second, but it gets its own name. It's called an ampere, or sometimes just an amp. We usually put a plus or a minus on the current if we want to indicate direction, and by direction we mean the direction that positive charge is flowing. And this can be confusing because a majority of the time it's actually electrons that are doing the flowing, that are actually moving, but they're negative. So if electrons are going one way down a wire, we actually define the current to be in the opposite direction, because that would be the equivalent positive charge is direction. I know it's confusing, but it's the way it needs to be to make everything work out. And then we talked about what's really going on. We said, if we talk about the usual case, when charge is flowing, which is free electrons moving in a conductor like a wire, what's mostly going on really is the electrons are bouncing around in random directions and moving very fast until they collide with an atom, and then they bounce off in some other random direction. And for the most part, that's the majority of the motion of each free electron, is just this random bouncing around. But when you do have a current, for whatever reason, some electric field is going to tend to push the electrons in one direction more than the other. That's sort of overlaying a slight trend in the direction of the current. Right, so I drew those pictures where you imagine the electron just bouncing around, but there's kind of an overall trend in one direction. As you see, I'm drawing. It's like over time trending in this direction, even though maybe only 45% of the time it's actually moving in that direction, or I should say 55% of the time, like sort of a slight majority of the time it has some component moving this way. And sometimes it's moving back this way if it bounced off an atom that way. But overall, it's going to sort of trend in the direction that we're calling the current. And that overall, the speed at which that trend is happening is called the drift velocity. And we connected that to the current with this formula, I equals NQ VdA. Vd is the drift velocity. In this formula, A is the cross-sectional area of the conductor, the wire. Q is the charge of each of the charge carriers, each of the things that have charge that are moving. As I've said, usually that's an electron, so usually that will be E, 1.60 times 10 to the minus 19. And N is a measure of how many electrons or charge carriers you have per cubic meter. Okay. Now, the reason that free electrons will move in a wire, in a conductor, is because for whatever reason, there's some electric field. And of course, when I say electric field, the energy way of looking at it is a changing V field, a potential difference. Okay, so there's some potential difference between, over two ends of a conductor. So I'll draw a wire. And whatever V is here, let's just make up numbers. V is 20 volts, V is 10 volts at this end. So there's a difference in the potential from one end to the other, right? That would mean that there's an electric field. The electric field always goes downhill, right? It goes from the higher to the lower. And therefore that would cause the electrons to move. Now the electrons are negative, so technically the electrons then would move this way. And I'm going to go back to just drawing them. We're going to go back to the simplistic picture of just drawing them as if they're just moving steadily this way. But again, remember, it's really this crazy chaotic motion with an overall trend toward that direction, right? And what I want to say here, and here's the important line, the higher the potential difference, the more current you'll have, the higher the current you'll have. You'll have more charge moving past any given point per second. Okay, because yeah, the drift velocity will be higher, and you'll get more charges passing any given point in the wire every second. Again, let me just point out that if the electrons are moving to the left, that's negative charge flowing to the left. The current would actually be defined toward the right, because that would be the equivalent positive charge. We kind of pretend that it's positive things moving to the right, even though really it's negative things moving to the left. Okay. So again, the higher the potential difference, the higher the current. And in fact, here's the definition of resistance. The resistance is the ratio of the potential difference to the current. And let me just talk about this definition just for a second. Imagine we had two wires, wire 1 and wire 2, and for both of them we put a potential difference of 10 volts onto them, a 10 volt difference from one end to the other, right? And now let's say in wire 1 the resulting current that we get is 5 amps, whereas in wire 2 the resulting current we get is 2.5 amps. Okay, so there's something different between these two wires, because we gave them the same potential difference, but they gave us different currents. Well, obviously we got more current in wire 1 than in current 2, so somehow wire 2 is more resistant to the flow of electricity, right? It's more resistant. The same amount of voltage didn't give us as much current. And that's what R is measuring. So if we do delta V divided by I, right, 10 volts divided by 5 amps, we get 2 volts per amp. Whereas here, the resistance, 10 volts divided by only 2.5 amps, that's 4 volts per amp. So more resistance here, more resistance here. And again, wire 2, for whatever reason, maybe it's made out of a different kind of metal, has more resistance, and that's why the same delta V gave us a smaller current. So that's the idea. That's the idea behind this definition. And let me just be clear that all conductors have some resistance. There's always a little bit of resistance to the motion, to the movement of charges. And what's going on there is that, you know, it's by and large, it's the atoms that the electrons are colliding into, which, as I keep drawing in those pictures, you know, sometimes means the electron will bounce back the other way. Even if there's generally a trend in one direction, the more colliding that is occurring will kind of slow it down. That makes sense, right? So there's always some amount of resistance. There's no such thing as a zero resistance conductor, except in very, very special cases. And I'll mention them right now. There is such a thing called a superconductor, in which the resistance does drop to 0, but that only happens for certain materials at incredibly low temperatures, very close to 0 Kelvin. Scientists, physicists have not been able to create a superconductor that works at room temperature or anything close to room temperature. Okay, so for the most part, so superconductors do exist, materials with 0 resistance, but for the most part, we don't deal with those on an everyday basis. So again, just to summarize, the electrons are colliding into the atoms that make up the conductor a lot, and that's, you know, slows them down, even if they generally move the way they're supposed to according to the current. And the measure of that is called resistance, and we quantify resistance this way. It's the ratio of how much voltage we're applying to the two ends of it divided by how much current we therefore cause to occur. Now, the units of resistance, well, we see that resistance is potential difference divided by current, and so that's going to be in volts per amp. But that gets a name as well. That gets its own name. It's called, well, the symbol is the capital Greek letter omega, which looks like that, and it's called an ohm. It's named after a German physicist named Georg Ohm, who lived in the early 1800s, and he was the first to really systematically study resistance. So this unit is named after him. So resistance is measured in ohms, but it's really volts per amp. Now, for many, in fact, well, for many conductors, if everything else is equal, everything else stays the same, resistance pretty much stays constant for any potential difference. And I'll explain that with numbers in a second, but just to say that another way, voltage and current are proportional. And that's called Ohm's Law. Ohm's Law. And substances that work that way are called ohmic. So it's sort of an adjective out of the word. Let me explain what I mean. So we said before, we had the example of a wire. We had two wires, but let me focus on that first wire. That first wire, we gave it a 10 volt potential difference from one side to the other, and the resulting current was 5 amps, I said, right? And so that meant that the resistance was, so the 10 volts divided by the 5 amps, so 2 volts per amp. I'll use the unit now, I'll call it 2 ohms, right? That was a 2 ohm, that was a resistance of 2 ohms. Now, let's say we have control over the delta V. We can choose what delta V to apply to the two ends of the wire. So if we double that to say 20 volts, if this wire is made out of an ohmic substance, the R is constant, the resistance is constant, so this will still be 2 ohms. So therefore, the delta V divided by the I still has to be 2, so this would be 10 amps. So in other words, when we doubled the voltage, we doubled the current. If we kicked it up to 50 volts, so times 10 from the original, then, or excuse me, times 5 times the original, then the current would be multiplied by 5, which would be 25 amps, still a 2 ohm resistance. So the delta V and then the I are proportional to each other the whole time. And you always get the same R. Right, so then you can, so R is a constant, delta V over I is constant. And typically that would, and typically in this case, R then would be a known thing, and you would figure out the I based on the delta V or vice versa, because you know the R. So it's nice when you know that a substance is ohmic, and most of the time we will assume that the conductor, the wire that we're talking about, is ohmic and obeys Ohm's law. At this point, let me just rewrite our definition of R so that it's, instead of division, it's multiplication. Let me bring the I over, right? So it would be delta V equals IR. For one thing, that's a little bit easier to write. We'll probably use it more often in that way. And the average person who knows about electronics, you know, for example, the average electrician, V equals IR is what they call Ohm's Law. Okay, so they actually call this equation Ohm's Law. Technically, that's not true, although it's totally fine that people call it that. The equation, this mathematical relationship is used all the time. It's really important, and it's nice to have a name for it. So a lot of people call this Ohm's Law. But technically it's not Ohm's Law. Really, this is just the definition of resistance. It's not a law, it's a definition. What Ohm's Law really is the fact that R is constant for a given conductor. That's what Ohm's Law, that's the law part of that. That's the thing that's not a definition, but something that has experimentally been figured out to be true, and we call it a law. But we won't quibble about that, and if you call this equation Ohm's Law, that's fine. The other thing is most people drop the delta in everyday life, which also is fine. Just as a shorthand, they refer to V as the change in potential between the two ends of the wire. Okay. Just to give one more kind of way to think about this, if we draw a graph and we put the change in potential down here, and kind of, at least for now, think of that, that's what we have control over. We're the ones who are setting the potential difference across the two ends of the wire, and then we observe what current we get out of the wire when we do that, right? So in an ohmic substance, or a substance that obeys Ohm's law, right, this is going to be a straight line. That's what proportional means, right? So y equals mx plus b, only the b is 0 here. Y equals mx. Delta v equals IR. And the m is is the slope, right? It's the constant, and here R is the slope. Except for one thing, m is multiplying x here, and usually x is the horizontal. In delta v equals IR, I have the constant multiplying I, but I made I the vertical axis here. So actually, if I swap this around just for, excuse me, I equals 1 over R delta V, that's the equation that kind of goes with this picture. So the slope here, the slope of this line, is 1 over R. But again, this is the equation you want to remember, but just in terms of thinking about this graph, the slope would be 1 over R, not R. If R is a measure of how resistant the wire is to letting a current flow, 1 over R would be kind of the reverse, right? That would be actually how good it is for a current, how much it supports a current, 1 over R. And in fact, 1 over R, if R is called the resistance, which it is, 1 over R is sometimes given the name conductance, right? So sort of a negative thing. R is sort of a negative thing, and 1 over R, the conductance, is sort of a positive thing, at least if you want a lot of current. Now there are substances that are not ohmic, that do not obey this law, and they kind of have a more of a curved graph. So there's not one slope, there's not one resistance. You can't do this. The table of numbers here would be very different and would be harder to predict for non-ohmic substances. Okay, so this would be non-ohmic. But like I said, most of the time we're going to assume we have ohmic substances and work with that. Okay. Now, if you have an actual electronic circuit, so a wire, that goes from some power source to maybe a couple of different electronic components, the thing it's actually trying to run, and then comes back to the power source. There's going to be resistance throughout that circuit, and the resistance comes from any components that are hooked up to the circuit, and then also the wire itself. As I mentioned, I said that all conductors, everything that electricity flows through, except for these special superconductors, everything else has some amount of resistance. So here's a little circuit that I'm just kind of comically drawing. A wire, and let's say this is your outlet, and of course an outlet has two prongs, right? And those are the two ends of your circuit. And of course, internally they go in and they connect up to your town's, electricity system, and they eventually, you can kind of think of them as, this is the power source that connects them. So of course, it's much bigger than that. It's your town's electricity system, but we'll just think of that as where the power's coming from and going to, basically creating a potential difference between the one end and the other end. And we have the wire going around in a big circle. Here's a light bulb that it's going to turn on, and then it comes back. Okay, so as current flows through this circuit, there is resistance, as I said, through the wire itself, and then at the light bulb. The light bulb itself actually will create the vast majority of the resistance in this circuit. And in fact, the wire comparatively will have very little resistance. The wire is a good conductor, and there is some resistance, but a lot less compared to the light bulb. So these are the two ways that resistance can come about, through any components hooked up to the circuit and the wire itself. The components generally are going to have a lot bigger resistance than the wire itself. And in some cases we can ignore the resistance of the wire. But I do want to talk about the resistance of the wire first. That's easy to get that out of the way. And so if we do think that we have to worry about the resistance of the wire, we want to know how to figure that out. So here we go. Wires have a relatively small amount of resistance. And what determines how much resistance the wire itself has? Well, it is proportional to the length. That makes sense. The longer the wire, the more resistance there will be, more chances for the electrons to collide with atoms, and actually inversely proportional to the cross-sectional area. So, and I'll talk about that in a second, but let me just write that down. So, proportional to the length, inversely proportional to the area. So length on top, area on bottom. And it's proportional, so there's some constant times L over A. And we're going to use the letter rho. Rho is commonly used. I know we've used rho in other situations. We've used rho for densities, but here it's a different use. And rho is called the resistivity of the material. So different kinds of metal will have different rhos, different values for the resistivity, and that's the kind of thing you look up in a table in your book or somewhere else. Okay, but beyond that comes like from what kind of material, and then you multiply by L, you divide by A. So I already mentioned it makes sense that it's proportional to length. The longer the wire, the more resistance there would be. But also inversely proportional to cross-sectional area. I think that also makes sense, because the thicker the wire is, there's more room for the electrons to flow, right? So that makes sense. A thinner wire, it's kind of it's more of a bottleneck, and there's going to be more resistance if it's really skinny. So the thicker the wire, you're going to be dividing by a bigger number here, and you'll get less resistance. Now there's one other variable that can play a role. In this equation, we make it seem as if rho is a constant, and we can treat it as a constant in some cases, but actually rho not only depends on what kind of material you have, but it also depends on temperature. So actually, the warmer things are, the warmer your material is, the more resistance there will be. And that also makes sense, because warmer, right, means more internal energy, which means those atoms are vibrating more. It is a solid, so they're, the atoms, the molecules themselves are mostly in place in a structure, but they do vibrate. That's the manifestation of internal energy, and hence temperature. So, and if they're vibrating more, you can imagine that if all the atoms are vibrating a lot more, that there's going to be more chance for an electron that's kind of coming through to run into them, because those vibrating atoms are going to sort of take up more space, so to speak, because they're vibrating, they're moving back and forth, right? So more chance for an electron that's trying to pass through to collide with them. So it kind of makes sense that warmer would mean more resistance. And we can quantify that. So here's the equation. So what you actually do, I mentioned that you look up rho on a table. What you actually look up in a table is rho naught, which is sort of a base resistivity. And that's the resistivity at 20 degrees Celsius. Or at least that's how the table in our book works. It gives you the resistivity at 20 degrees Celsius. And so you see there's a 20 degrees Celsius in this equation. Now whatever temperature your wire is at, you plug that in here. You multiply by the coefficient alpha, which goes along with your type of material, and again you look that up, and that will be an actual constant. Add 1 and multiply it by the rho naught, and that'll give you the rho at your temperature. So just threw some equations at you. Let's try this out. Let's suppose we have a wire that's 4 meters long. It has a diameter of 6 millimeters, and it's made out of silver. Question A, at 20 degrees Celsius, so that's sort of our base temperature, what would be the resistance of this wire? And how much current would flow through it if a potential difference of 23 volts is applied across it? And we're going to assume nothing else is attached, no light bulbs or any other electronic components, because of course that would change the current as well. It's just the wire. Okay, so here's the 4-meter wire, and let's figure out the resistance. So the resistivity at 20 degrees Celsius, I look that up, and for silver it is 1.62 times 10 to the negative 8th, and that's actually in ohm meters. Turns out that that's the right unit for this resistivity. Okay, so now I know that the resistance of a wire is my resistivity times L over A. So I put in the resistivity. I multiply by my 4 meters, and I divide by my area. Now my area, if you're not told otherwise, assume wires are circular. And we've got a 6 millimeter diameter, so that's a 3 millimeter radius. So that would be pi r squared, right? Pi times 0.00300 meters squared. And you can see that we'll have meters on top, we'll have meters squared on bottom, so but we have another meter here in the resistivity, so the meters all cancel and we'll be left with ohms. And this turns out to be 0.00229 ohms, 2.29 milliohms. And you'll see when we do some when we look at resistors, which are made to have a lot more resistance, this is a small amount of resistance. And that is the point, that we're figuring out the resistance of a wire, but if anything else is involved, it probably is going to create, like a light bulb will create a lot more resistance, and this is almost negligible. Okay, but we're figuring it out. So that's that's the first part of part A. Now, for the rest of part A, now let's assume that we put a 23 volt difference across this. So we set things up using our power source, using a battery or whatever, so that the potential difference is 23 volts higher on one end versus the other. And so that's creating a voltage, that's creating an electric field going from the higher to the lower, and we're going to get electrons to start moving, and we're going to get a current. So now we go to delta V equals I R. And we're actually going to use it, we want to get I, right? So I is delta V divided by R. So 23 volts divided by 2.29 milliohms is Well, to 3 significant figures, it's 10,000 amps, which is a lot of current. A lot of current. So it's because there's so little resistance. So it doesn't take much voltage to create a lot of current when you don't have any resistance. When you don't have any major resistive components in the circuit, you're going to get a lot of current. So 10,000 amps. Okay, now let's redo the question, but let's do it at 100 degrees Celsius. And all that's going to do is it's just going to change this first number. Okay, so my new resistivity for silver at 100 degrees is that base number, but now times this factor of 1 plus alpha T minus 20 degrees Celsius. So I've got my base one already, 1.62 times 10 to the negative 8th ohm meters. And then we're going to multiply that by 1 plus, and now I have to look up the alpha, the temperature coefficient for silver. And that is, again, this is just something you look up. It's experimentally figured out for various conductors. 4.1 times 10 to the minus 3, and that's in inverse degrees Celsius or Kelvin. Times, and then T minus 20. Basically, how many degrees above 20 degrees are you? So we're at 100, so that's 80. And remember, when you're talking about a temperature change like we are, it doesn't matter if it's Kelvin or degrees Celsius. So degrees Celsius and Kelvin will cancel here. Okay, and that gives us a new row, a new resistivity of 2.15 times 10 to the negative 8 ohm meters. So you see it went up by, a certain amount, like a 30% increase or something like that. Okay, so that's our new row. So now we figure out the new resistance of the wire at this temperature. So same calculation, just replace this number, right, with 2.15. And now we get 0.00304 ohms, 3.04 milliohms. So a little bit bigger. Again, we're talking about small resistance here. We're in the milliohm territory, but it's gone up because of the temperature increase. All right, now we apply the 23 volt potential difference and get electrons to start flowing, and we get a current of to 3 significant figures would be 7,560 amps. Still a lot of current, but you see it's gone down because we had more resistance because the temperature went up. Okay, so there's a quick example of, or not so quick, but example of using V equals IR first of all, but also figuring out the resistance of just a wire. And again, wires themselves, they're meant to facilitate electricity flowing, so they have low resistances, as you see. And if that's all you have, if you don't have anything else involved, if you just have the wire, it doesn't take much voltage to create large currents in the thousands of amps. Now, because of that, because you see that we get these really large currents, in fact, dangerously large currents, those currents are too big usually for the operation of most electronic devices. And so you need to tamper that down. We need to reduce the amount of current. And so if the wire itself is not doing the job because it has such small resistance, there are devices that are put into circuits whose job is simply to supply a good chunk of resistance, and they're called resistors. And you see this is actually what they look like. And you can open up electronic devices and see things like this. And yeah, their sole job is to add resistance in order to decrease the current. With resistors, it's going to be simple. A resistor simply has a known amount of resistance. They're built that way. And so there's no formula for it unless you're the one creating the resistor, which we're not going to get involved in. The resistance is going to be a lot more. sort of, instead of in milliohms, it's going to be in ohms. So, 1,000 times bigger potentially than the resistance of the wire that it's connected to. And when you have these resistors in your circuit, like I said, they're 1,000 times bigger. So in that case, you can kind of forget about the resistance of the wire. I mean, technically, you should add that resistance in as well. But yeah, it's going to be it's going to be negligible comparatively. So you can kind of proceed without even worrying about the resistance of the wire itself if you have one of these resistors or more than one resistor in your circuit. Let me give you a few important facts and things to know about resistors. The first thing is, so we're going to start getting into drawing pictures of circuits, and usually we draw wires just as straight lines, of course. For a resistor, we don't try to be artists and actually draw a resistor like you saw in these pictures. What people have done is they've developed a system of symbols, and for a resistor, the way we draw a resistor is a little jagged line like this. So that's what a resistor looks like in a circuit. And as we proceed, I'll show you. We'll also learn how to draw in batteries. Because we're not going to get into too much electronics, that's pretty much it. But all the different components in circuits have their own symbol. So a little just sort of zigzag line in the middle of a wire represents a resistor has been placed there. Okay. So again, I've already said this, but just the big fact about resistors is that they limit the current in the circuit. They do that by adding a good amount of resistance, and that is their purpose. What's important to understand is that they limit the current, but it's not like what you don't want to think of is that the current is big coming in and then it hits the resistor and then it's small on the other side. That's not the way this works. If the resistor is in the circuit, then the current overall will be less on both sides of it. Think of it this way. Think of water flowing through a pipe. And think of the resistor as a real, like all of a sudden the pipe gets really skinny and then it gets big again. So that's kind of like the analog of the resistor. Well, it's not like the water, and then if you have water flowing through this pipe, it's not like the water is going really fast and then it slows down here. Of course, it couldn't do that because there'd be a backup because the water, so many cubic meters of water would be coming in, but less would be going out because it's going slower. That wouldn't work. The pipe would burst. What, of course, has to happen is that it has to slow down back here, too. So it slows down everywhere. One bottleneck causes it to slow down everywhere. Or like in a traffic jam, right? It's a traffic jam, like say I-95 is cut down to one lane in one place. Of course, that'll slow down traffic before where the construction is. That's actually a bad analogy because then once you're through, you can go faster. Think of the water example. I think the water example is better. On both sides of the bottleneck, things have to slow down. So similarly, on both sides of the resistor, the current has to slow down. It has to be less current. Delta V equals IR is operational here. And so the potential drops on from one side of the resistor to the other side of the resistor by quite a bit. Right? So you may have applied a potential difference from one side of the wire to the other side. So maybe if I do a little V scale. On this side of the wire it's really high, and by the time you get to the other side it's lower, right? And that's of course the whole point of what we're talking about is that change in V is what is causing current to flow. Well, that V will go pretty much, it'll only drop a little bit as we go along the wire, and that's because there's not much resistance there. And then right at the resistor, it'll drop a lot. And then Again, for the rest of the wire, it'll just drop a tiny, tiny, tiny bit until it gets there. So the drop in voltage from one side to the other is almost all happening right at the resistor. Okay, so that's what I want you to think of in terms of delta V. Okay, and you can measure it. Delta V equals IR. So you have the R for the resistor times the current of the whole thing. Remember, that's what we said in point 2, is that there's one current for this whole wire from beginning to end. Okay, and so the delta V drops right where the resistance sort of occurs. All right. And then the last thing I want to point out, and this is what we'll pick up in our next class, resistors sap energy from the system. So we haven't brought energy into it, and of course that's the whole point of electronic circuits, is sort of an energy delivery system to some device. So resistors do take energy out of the system. They convert it into internal energy. Just a straight up resistor will heat up. So it'll turn the electric energy that's in the circuit, and it'll just transmit it out as heat and radiation to the environment. It'll heat up the air around it. It'll radiate. It won't get so hot that it will glow. It won't be that kind of visible radiation, but it will radiate some non-visible radiation into the environment. And we'll talk more about that. Other things that have resistance, like a light bulb. A light bulb is not a resistor, but it has a lot of resistance like a resistor does. And of course, it would turn its energy into light, mostly, which is what its whole point, right? That's what it's supposed to do. Okay, so things that have a lot of resistance also take energy out of the system, either in a wasteful way or in a useful way. We will get more into that in the next class. Okay, but you've now learned the basics on resistance and resistors.